Hello and welcome to Night School. I'm Aria.
And I'm Darian.
And every month, we here on Night School bring together scientists, artists, and creators to dig into a new theme. And tonight, we're looking up. Like, not literally, technically, we're looking forward at the computer, but metaphorically up. And tonight, our guests have spent countless hours looking to the night skies, discovering new planets, killing old ones, and even acting as intergalactic tour guides. And it's been a little while since we've explored space here on Night School, and friends watching, Darian and I are right there with you, wide-eyed in awe and maybe a touch of existential dread when it comes to thinking about the massive expanse that is our universe. But we're very excited to have some amazing guests tonight and to learn from them. So who are we hearing from?
Well, we're starting out our night of the night sky with Caprice Phillips, a PhD candidate from the Ohio State University, who works to discover and describe planets many light years away in far-off solar systems. Caprice will walk us through how she uses uber-powerful telescopes to scan stars for signs of planets, including some that may host extraterrestrial life. I believe that this is going to be one stellar presentation. Next, we're going to bring it back into our own solar system in our neighborhood. When I was in grade school, I memorized the planets using my very educated mother just served us 9 pizzas. And then one year, all of my teachers were like, just kidding. And then 9 pizzas turned into like noodles or nachos. I forget. But tonight we will hear from Mike Brown, the astronomer responsible for this, the man who killed Pluto, or maybe more accurately, the man who reclassified it as a dwarf planet. Now, based on recent evidence, though, he's searching for a new giant planet beyond Neptune, and he'll let us know if this time we can prove the presence of Planet 9. And then lastly, I hope you're all wearing seatbelts because the Academy's own Christian Contreras will be guiding us on a journey, zooming faster than the speed of light into the furthest reaches of the known universe. Using OpenSpace, a software developed by NASA and used at our own Morrison Planetarium, Christian will give us a tour of everything. Literally everything in the universe that humans have been able to perceive unfathomably far into outer space and get us back in time for dinner. No big deal.
Fantastic. That's what I need. And always, as always, tonight's program is live. So whether you're looking /up with us tonight on YouTube, Facebook, or Twitch, say hi. Let us know from where in the world or the galaxy you're watching from, whether it's your first time joining us or you're a Night School regular. We are so happy that you're here. And we do have a Q&A session after every presenter. So if you have any questions, comments, thoughts, feelings about how big and vast the universe really is, drop them in the comments or the chat and we'll pass them along. And with that, we'll kick it over to Caprice.
Okay, so hi everyone. Thank y'all for the introduction. So as I said, my name's Caprice Phillips. My pronouns are she, her, and hers, and I'm a grad student at the Ohio State University. So kind of today, tonight, I guess I wanted to walk y'all through kind of searching for exoplanets and how and where we might look in the era of these next generation and current telescopes such as JWST. So I kind of wanted to start this kind of talk and little introduction with this quote that I really like by Plato, which reads, like astronomy compels the soul to look upwards. We talked about looking up or at the computer and leads us from this world to another. And so I think that this is a very powerful quote. And one thing is that the same is true for me, like looking upward at the night sky is what got me started interested in science and astronomy in general. And also, we don't know for certain what Plato was referring to when he said to another, but we can kind of think as to another may refer to celestial bodies or worlds beyond ours. So one of the things I really like about astronomy is that it's one of the world's oldest scientists. Folks have used astronomy for kind of cultural reasons, measuring time, cycles, seasons. And it's influenced us from the landing of the first people on the moon to the naming of like Mars candy bar, like for example. And so kind of there are these longing questions of humanity, such as, are we alone? Does life exist outside of our solar system? And like, do other Earths exist? And do they have signs of life? And those are some of the driving things that drives astronomical research, and in particular, some of the things that I've worked on in graduate school. So as I just wanted to give like a little journey, and as we kind of like go through this, I wanted to kind of talk about one of the things that I study are exoplanets, which are planets that are outside of our solar system, or they're also a longer name for extrasolar planets. And so one of the ways, we're trying to identify and find different types of exoplanets, but there's kind of a question of like, how do we even look for these planets, these exoplanets in the first place? So here a plot, I grabbed this from the NASA Exoplanet Archive. So this is a plot showing like the cumulative number of detections of exoplanets by discovery year. And the different color codeds are like different ways they've been detected, for example. And so what I really like about this plot is kind of showing how it went from like slowly not really having anything to just being like, oh, we think they're out there. So we have this kind of boom and introduction of these detection of these first exoplanets. And then like you go to like 2023 here, and like we're, near and past 5,000 exoplanets that we've detected and confirmed so far. And so we, in 2009, we really see this kind of increase in the number of exoplanet detections, and that's due to something that's called the Kepler space mission. And so is this space telescope that was designed to survey a portion of the Milky Way galaxy in search for exoplanets. So we started seeing a lot of planets being detected with this particular telescope. So I mentioned before, like, so since the discovery of the first exoplanets, and the first one around like a sun-like star was in 1995, but there was actually a planet discovered in 1992, but it was around like a pulsar, a dying star, and it was being bathed in radiation. So it wasn't as a hot topic as the one where they found around a more of a sun-like star like our own. 51 Peg B. And so since that those discoveries in 1992 and 1995, you've actually discovered 5,000 plus exoplanets so far. And we found small rocky worlds like Earth, like gas giants, many times larger than Jupiter. We found hot Jupiter, which are in scorching close orbits around their stars. Like we found super Earths, which are possibly rocky worlds bigger than our own. And we found mini Neptunes, which are smaller versions of our solar system's Neptune. And so, you kind of add to that mix, we found stars like planets orbiting two stars at once, and planets orbiting collapsed remnants of dead stars. And so what's really interesting about this is the diversity of planets that we found so far just within our own galaxy. And so when you think about like, okay, so how have we actually found these planets? Like looking for planets is not something that's very easy, but scientists have like kind of come up with like these ways. They're like, okay, this is a good way of trying to find like another planet, like orbiting another star outside of our galaxy. So one of the ways that astronomers have done this is something called the transit method, which is something also known as dip of brightness. So basically, this is what the Kepler mission did. It stared at a large portion of the sky, and it stared at a bunch of stars, and it looked for a dip in the brightness of a star, which can be indication that something is crossing in front of it or causing the dip in brightness. And so, if you're trying to look at a smaller planet around a bigger star, you get you get a smaller dip, versus if you're looking at the same size planet around a smaller star, you get like a bigger dip. So folks will like look at stars and see if there's something causing a dip in the brightness, and it could be a sign that something is orbiting and causing it to dip. So that's one method. The primary method that exoplanets have been detected by is this transit method of detection, and that's challenging in itself. So another way that people have tried to search for exoplanets is actually by taking direct image of them with really powerful cameras, either from the ground or from space, for example. Like we can't do this with like just the powerful cameras on our cell phones, you need something with a really, really large kind of aperture. And so direct imaging transits are hard, but direct imaging is very hard. There's only a handful of like planets that have been discovered. So less than 2% have been like directly imaged, for example. And so this method is very challenging because you want to remove the overwearing glare. Stars are so bright. You want to remove that glare of the star in order to be able to find a planet possibly orbiting around it. And so one of the cool analogies for this is something called the lighthouse analogy. So basically, this is like the equivalent of trying to spot a tiny firefly going around a lighthouse from like miles away. Like first, you're gonna want to try to turn off the light in the first place to spot that firefly. And so scientists do this with something called a coronagraph. They block out the starlight to be able to try to find that little firefly or planet in the first place. And this can be done with the right conditions and using special tools and techniques. So these two are some of the ways that folks have used to detect exoplanets. There are other ways, but I thought these are some of the most like intuitive and cooler ways of trying to detect exoplanets that I wanted to highlight. But there are many other ways that folks are trying to do this, like radial velocity, kind of trying to see the motions that other like planets may have on their stars, for example, and something called gravitational microlensing as well. And so I wanted to show this image because I thought it was a really cool image of a exoplanet taken with JWST. For example, in the different pictures, it's the same kind of planet, but it's a thing in like different like instruments and filters of the same kind of planet, just with different like kind of instruments and setups with instruments aboard JWST. And so, kind of the next question that we want to, the scientists are looking at, like, where do we even try to look for exoplanets, or even try to look for potential signs of life? Like, we discovered all these 5,000 exoplanets, but like, where special do we want to try to find them? And then also one of the other questions is, how hard is it to find another Earth-like planet in the first place? So, kind of starting out, we scientists want to look for something called the habitable zone. So, basically, this is kind of a first order idea. Is that is either it's called the habitable zone or the Goldilocks zone, where you want to look for a planet at the right distance from its host star, where it can host like liquid water, for example. Like too close to its star, like the water may like evaporate like off the planet, but too far it may be frozen. For example, like the Earth is in the habitable zone of our star, and so we want to find something that's similar to that, and we want to kind of ask like, is this kind of configuration unique, for example? And so, what's really interesting about the habitable zone is that it looks different for different types of stars. So, if you have like a sun-like star, like our star here, you're going to have a certain zone where it's not really ideal to be, and then the green is like the habitable zone, and the kind of blue is kind of where it gets frozen out. But if you have a hotter star, you need to be further away from that star in order to have a habitable zone. Versus if you have a cooler star, like a red dwarf or an M-type star, you can actually be like closer to your star, like with your habitable zone. So this can vary depending on the type of star and brightness and energy output that that star is given. And so we've discovered lots of exoplanets, and we're looking for ones that are in the habitable zone, for example, as a first order pass for things. So we have something called like the exoplanet zoo, for example. And so we found such a variety of planets. And it's like, for example, one of the ones we found is the one called, it's like K218b, where it was the first planet in the habitable zone of its host star that was found with traces of water vapor in its atmosphere. And that was with the Hubble Space Telescope. And that was the first time in 2019. We also have, for example, the TRAPPIST one system. There, this system of I think like 6 or 7 planets that are like Earth size that are kind of orbiting a very very small star, for example. And this is just an artist illustration of what that looks like. And so this is another like illustration kind of showing like basically if we were to take this system configuration and into our own solar system, they be closer into orbit than like Mercury is, which is the closest planet in our solar system to the sun. Like they're like that close to their host star. So there's really interesting like things about like can these planets maintain an atmosphere and different things like that, and like and some of them are also in their own habitable zone for that star. And so another one that I wanted to talk about is something called Proxima Centauri b, which is our nearest neighbor. And so it's in the habitable zone for its host star, but we kind of have to be careful when we talk about like, oh, if it's in the habitable zone, like just because something is in the habitable zone doesn't mean that it's habitable. Um, exactly, it just means that it may be able to maintain liquid water like on its surface, but you want to ask questions like, does it actually have an atmosphere? Like, atmosphere is a vital for like circulation on the planet, and it's essential for life as we know it. For example, so having the right kind of atmosphere and just having one in general is also a marker of something to be able to be habitable as well. And so, like I mentioned, like we've discovered all these worlds, but are they truly habitable? And so I wanted to show this plot kind of showing like the center is liquid water, and the different things around here are all the things that can go into having liquid water. For example, like we need to know things about its interior, its atmosphere, its surface, the planetary system, the stellar effects. And these are all the things you have to consider when you think about like, can this planet maintain like water on its liquid surface? Like all these different things go into kind of defining and understanding that criteria. And so as I get closer to wrapping up here, I wanted to go back to inhabited Earth. So in our atmosphere, like it's mostly composed of nitrogen and oxygen with traces of other gas species, and we have something called an oxidizing atmosphere. However, all the exoplanets don't have atmosphere. Not all exoplanets have atmospheres that look like this. They can have atmospheres of mainly like hydrogen, for example. And so the presence of hydrogen in this atmosphere creates something called a reducing atmosphere, where we can have like predominance of different molecules such as water, ammonia, and methane, and that's really in contrast to the atmosphere that we have here on Earth, for example. And so that can bring about different signs of life or potential biosignatures. And so this is just an artist's illustration of how such atmosphere or planet may look like, with like primarily atmosphere being made in hydrogen and helium, with maybe a liquid water ocean underneath with a silicate crust. And so one of those things that I've been studying is ammonia as a potential biosignature. And so the idea is that ammonia can be a potential biosignature in planets that have atmospheres that are hydrogen and nitrogen dominated, as opposed to like nitrogen and oxygen dominated here on Earth. And so the different chemical reactions can cause this biosignature to appear. Like these microbes can break apart the bonds in the nitrogen and hydrogen in the atmosphere, for example. And there can be an excess buildup where we can detect ammonia in the atmosphere. And that's been something I've been looking at, see if we can detect that with JWST as well. And so one of the things that I look at and see is if we can like use these big telescopes like JWST to detect ammonia in the atmospheres of these planets. But I have this big list of questions up here that's basically like a precaution, because you don't want to just be like, we found ammonia, we found signs of life. There are so many other things that you have to take into consideration. Like, what does the detection mean? Can we actually detect it? How long does hydrogen last in the atmosphere, for example? So it brings in a lot of interdisciplinary nature for this type of research, which I really enjoy. And so this is just a plot just showing like, how we might go about detecting this atmosphere. This is just kind of showing a simulated atmosphere with how the simulations for the observations would look with different instruments aboard JODIS-T, and like the corresponding like detection significance on the bottom. And this is some example of some of the plots that I make for the type of work that I work on to see which planets might be best for this type of detection. And so I didn't want to go too much over time, but I wanted to kind of leave y'all with this quote that I really like, that there are infinite worlds both and unlike this world of ours. We must believe that in all the worlds there are living creatures and plants and other things we see um, in this world. And I guess with that, like, I can take any Q&A questions. Sorry, I know I went through a lot, but I get really excited about these types of things. So yeah.
Hey, Caprice, that was great. Thanks so much. And we have lots and lots of great questions coming in from our audience, so I'll just like get right into it.
Mhm.
The first one, like, can you tell us more about what JWST is? And like, it sounds like every astronomer on Earth would probably want to use something like that as a tool. Is there a wait list asking for a friend?
Yeah, so that's a great question. It's whoever answered it. So JWST stands for like the James Webb Space Telescope. It was launched, I think about like a year ago. Sorry, time is like so spacey right now. But it was launched like on Christmas, either last year or year before that. I can't exactly remember. But it's this next generation telescope that's been in planning for many, many years. That's currently, it was launched into space, and it has a really big mirror and has really powerful like instruments that's able to kind of probe more wavelengths coverage, so we're able to learn about more different kind of molecules in the atmosphere. We're able to scan these different types of exoplanets like in the TRAPPIST system to see if we're even able to see if they have an atmosphere in the first place. So it's a really powerful telescope that like every astronomer that like does observation really wants to use. You have to go like propose to get time on it. It's super competitive and everything, to be able to use this really powerful kind of instrument that's really going to continue to shape like astronomy and let us know like what we know and what we don't know. So
Yeah, absolutely. It sounds like amazing what a big mirror can do in the sky, huh? Like,
yeah, it's crazy. Like you just need like a really big like aperture and whatever to like capture the light. So it's pretty awesome. I'm a little biased, but I think it's cool.
yeah. No, I'm right there with you. And so it seems like 5,000 plus exoplanets. That's a lot of planets. And Lori from our audience is wondering like what does it look like to collaborate on astronomy worldwide? Like, are there people working together like everywhere to describe these?
Yeah, no, that's a great question too. Like one of the things that I actually really love about astronomy is that it is the like it's a worldwide science. Like I collaborate with folks like in Europe, like there are folks that have like collaborators like in the Philippines, like there are people that there are telescopes in Africa, like they're all over. There's many different kinds, and so it's like potential, especially with like looking for biosignatures or potential signs of other life. Like it's so interdisciplinary that astronomers, like we need to talk to like planetary scientists, chemists, biologists, like all these folks to like get a sense of like if we were to detect this potential signs of life, like what does it mean? Like we got to bring in other experts. So we do work with quite a large array of folks. So.
Yeah, that's amazing. Did you go straight into the field that you're in right now? Like, do you come from like a specifically astronomy background?
Oh yeah, so I originally like I came from like a physics background, but someone told me that astronomy is nothing more than like physics and space, and so like that's like the background that I came in, and I went into grad school to do astronomy. But I knew that I wanted to do like astronomy pretty early on. Like as a child in my 8th grade yearbook, I wrote that my career thing will be like astronomer. I spelled it horribly wrong. I still spelled out astronomer. You know what I'm saying? So
It still
that
counts.
yeah, they still count. I have a picture of it. I still have that yearbook.
Oh, amazing. That's
Yeah.
fantastic. And okay, so Martin is asking all of those like liquid water characteristics that you showed, like can how many of those can we like detect right now and like what does that look like?
Yeah, so that is y'all asking some great questions. So no, that's really good. So in that plot that I showed, I went through it really fast, but there are actually, it's like color coded. One's like orange or then green or something, and some of them are some of the things that we can directly observe. Like we can try to see if there's an atmosphere, like for example, by using like spectroscopy. And then there are other things where we need models to understand. Like we can't directly observe that. We have to like use some inference or some observation to try to inform the models to learn about things. So there are things that we can directly observe, but there are like some things that like we literally like cannot like see or whatever. We have to use models to try to understand that, which makes it even more cool because then you get to work with observers, theorists, and models. So it's just like a cornucopia of things. So yeah.
Yeah, amazing. And kind of
Yeah.
along those lines of things that are harder to find, like, is it harder to find like smaller rocky exoplanets? Like when you were showing that transit method, it looked like, like there are some like small planet. Like, is that why there are so few of those relative to those gas giants?
Yeah, no, it's actually very hard to find like Earth-sized planets. Like if someone like if like an intelligent life was like looking at our solar system, like it'd be really hard to see like transit, to see such a small planet relative to such a big star like making a different brightness. It's very small. You wouldn't be able to really detect that. And if you were trying to take a direct image of it, like our star, like that lighthouse analogy, right? Like it's going to be like overwhelming, like any kind of signature from Earth, for example, which makes it so hard to find these smaller Earth-sized planets. But there are upcoming telescopes that are going to try to do that, like the Roman Space Telescope, to look for more planets like that. But it's very, very challenging to do given how bright and the stars are and how small these planets are.
Yeah,
Yeah.
amazing. And then one final quick question.
Mhm.
Do you have a favorite exoplanet and why?
Do I have a favorite exoplanet? So I'm a little I'm I'm a little biased. So one of my actual favorite planets is I think is like Neptune, that's in our own solar system, because I think whenever I was really getting interested into astronomy, my favorite color is blue, and so like the planet Neptune was like so like blue and cool and rich, and I was like, this is really interesting, and so like that's what like helped like drive me like into astronomy, was just how cool it looked. So like I'm a little biased that my favorite one is like actually like probably like within our own solar system. There's a student, Ashley Walker, that does ice giants, and so she's like, I'm the ice giant queen, and Neptune like falls into that. So
So
yeah.
powerful. Ice giant.
Yeah.
I love it. Well, thank you so much for your presentation tonight. It was great to hear from you. And we're going to go ahead and bring up Mike next.
Cool. Thank you.
Hey, everybody. I'm Mike Brown. I'm an astronomer at Caltech here in Pasadena, California. And I'm going to pull you back from thinking about all those amazing exoplanets that Caprice was talking about and pull you back into our own solar system. And to begin with, I'm going to actually pull you back at about 250 years. If you were around 250 years ago and you went outside and you looked at the sky, you could see every planet. You could see Mercury, you could see Venus, you could look down and see the Earth. You could see Mars. You could see Jupiter. You could see Saturn. Well, that's it. That was the last one. You could see Saturn. Those were all the planets that were known. It took until 1781. William Herschel, astronomer, was looking at the night sky. He was mapping out the positions of stars with his fancy new telescope. It's always about the fancy new telescopes, even then, as now. And he found this one kind of blob that was a little bit, it didn't quite look like a crisp little star. It looked like a blob. And he wasn't quite sure what it was. So he came back and looked at it the next night, and it moved. It was not in the same position as it had been the night before. As soon as you see something that moves, you know that you found something in the solar system. But it moved so slowly, it had to be really far away. It had to be further away than Saturn, than the most distant planet. And Herschel actually didn't know what to call it. He thought maybe it was a comet because we knew about comets at the time. Other people started saying, hey, Herschel, that's a planet. And he was like, no, man, that's not a planet. It's just a comet. It's a something. After a while, he finally became convinced that this thing he had found might really be a planet. He gave it a name, named it George. That didn't stick. But people were still not really sure if it was a planet that was past Saturn or a comet that was going to come in closer. It was really hard to tell. It took actually another many years before an astronomer, Alexis Bouvard, wrote this very dry and fascinating book on tables, astronomical tables of longitudes of Jupiter, Saturn, and Uranus. Uranus was, of course, the name that George became. And in these tables, what Bouvard had done was to look at the position of that where astronomers had seen Uranus. He took the positions of Jupiter and Saturn, and he calculated the gravitational pulls of Jupiter and Saturn and where Uranus was, and he showed that Uranus is in a beautiful circular orbit around the sun, just like a planet. It didn't come in close like a comet. It stayed beyond Saturn the entire time. This was 1821, as you can see here, and that was it. It took those 40 years before it was really convinced that Uranus was a planet. It was a bunch of math to show exactly where it should be, but there's most fascinating is there's this table. And so if you want to look at this table carefully, there's the discovery date, 1781, all of these observations after the discovery, and a bunch of numbers, pluses and minuses. And these are how far from Bouvard's prediction the planet is. Sometimes it's a little in front, sometimes a little behind, back to in front. But what's also fascinating is there are observations for more than 100 years before the discovery of Uranus. Uranus was first actually seen in 1690 by accident, but no one ever did what Herschel did, which was to look at it one night, come back and seen it the next night and see that it moved. If it had been done in 1690 by Flamsteed, he would have been the discoverer of Uranus way back then. Bouvard went back and tracked down those observations and figure out where it was. But he had this great theory, be little in front, little behind, and he has this great quote. It's in French, but basically he says, "I have done the calculations. My theory is perfect because I am the smartest astronomer around. And so the fact that there are these deviations proves that astronomers are doing a poor job of measuring things and they need to do better." The astronomers felt very admonished and they went back to their drawing boards. And starting in 1820, they made more and more precise observations, and Uranus was still in the wrong spot. And it turns out by about 1840, everybody understood that the reason Uranus was in the wrong spot was because something was tugging at it besides Jupiter and Saturn. And that thing tugging at it was another planet beyond Uranus. Everybody knew it was out there, but nobody knew quite how to find it until another French astronomer working in the same place as Bouvard at the observatory in Paris, figured out mathematically how you could use these very data, a little in front, a little behind, to predict the location of a new planet beyond Uranus. He predicted this location. He sent his prediction to the observatory in Berlin. One September evening in 1845, they opened up the telescope. And it was right there. That was Neptune. They found Neptune in like half of a night after the prediction of where it should be. It was one of the most amazing feats of prediction and discovery, I think, still in science today. And of course, Bouvard got very famous. He was the astronomer who found a planet at the tip of his pencil. Everybody wanted to get into the act, and everybody started predicting new planets. There's a planet here. There's a planet there. They were all wrong, but the most famous of the wrong ones was the American astronomer Percival Lowell. Percival Lowell predicted planet P, then Q, then R, then S, then T, then U, then V, then W, and finally his final prediction was planet X. Everybody's heard of planet X. Everybody thinks the X stands for 10 or unknown. It really was just Lowell's prediction of where it should be. He sent a team of astronomers up to Mount Wilson Observatory. Mount Wilson is a mountain right above Pasadena, California. If you look that way, you could see it. It's right there. I could almost see the observatory up there. And they took a picture of the sky looking for planet X, and there it is somewhere. Maybe, maybe it's not there. They took a picture that looked like a lot like this, and Lowell looked at it and was like, I don't know, is there a planet there? Maybe yes, maybe no. Lowell eventually passed away before anything was found, was very disappointed. But in the meantime, he founded the Lowell Observatory in Flagstaff. And at that observatory, they built a telescope dedicated to finding this planet X. They hired Clyde Tombaugh off the farm in Illinois. And in 1930, it started in 1929. 1930, Clyde Tombaugh was taking images. He took images just like this one. And he said, I don't know, how do I even know if any of these dots is a planet? I know. I'll do like Herschel, and I'll take a picture the next night, and I'll watch it move. Did you guys watch it move? Maybe. Okay, let's try again. Here's the first night. Here's the second night. Anybody see it? Nope. Let's try it again. First night, second night. Oh, wait, you saw it. That was it. These are actually the discovery images of Pluto itself from 1930 from Percival Lowell. And it's this tiny, tiny little thing out there. And it was not the planet X that astronomers were looking for. Planet X, the alleged planet X, was supposed to be the mass of Jupiter or larger. And this is something like 250,000 times smaller than that. But astronomers didn't know that at the time, so they called it a planet, and it stayed a planet in good standing, even though it is tiny. We now know. Here's the sizes of all the planets: Jupiter, Saturn, Uranus, Neptune, the terrestrial planets here, even little asteroids. There's Pluto, tiny little, I'll say the word, pathetic Pluto that barely can be seen on the screen. Doesn't fit what the rest of the planets look like. Really made no sense, and it makes even less sense when you look at it in the context of the orbits of the other planets. Here are the orbits: terrestrial planets: Jupiter, Saturn, Uranus, Neptune. Put Pluto on there. It doesn't even go on a circular orbit. It dips inside the orbit of Neptune for a while. If you tilt it on its side, you see that while the planets are all in one disk going around the sun, Pluto is tilted about 20 degrees. It just really made no sense. Too small, too weird. But for many years, for 60 years, it was just called an oddball on the edge of the solar system. That all changed in 1992 with the first discovery of another object beyond Neptune, and then another, and then another, and then another. And as of today, there are something like 2,000 objects known with orbits beyond the orbit of Neptune in this region that we call the Kuiper Belt. And if you look at their orbits, they are like Pluto. They're tilted in one direction, tilted in the other direction, stretched out this way, stretched out that way. Some of them cross the orbit of Neptune, some of them don't cross the orbit of Neptune. But even back when these were first being discovered, when Pluto was still called a planet, it was very clear that Pluto is part of this population and should not have been considered part of the planetary population. What's interesting, though, is that with this population in place, we also had a great way of trying to see if there were any other new planets beyond Neptune. Neptune, originally Planet X was being looked for because people thought that there were new planets, thought that Neptune was being perturbed. And it turned out Neptune is not being perturbed. Those observations were just wrong. Bouvard was actually right in 1820. Astronomers did need to make better observations. And when they did, they realized Neptune is exactly in the right place. Uranus is exactly in the right place. All of the Kuiper Belt objects out there make sense. There is no need for anything else in the entire solar system besides what we knew, or at least that was true until 2003. In 2003, hard for me to believe this was 20 years ago now. This was one of the more exciting discoveries that I have made in my career. We found this object. I'm going to go back to this one. We found this object called Sedna. Sedna is on an orbit that is so distant from the solar system that it never even comes close to the rest of the Kuiper Belt. It takes 10,000 years to go around the sun, and you cannot make an orbit like this without something else in the solar system causing it. And back in 2003, we thought we knew the answer. We thought actually that this formed this way because of another star besides the sun. Another star came screaming through the solar system and pushed around some of the orbits and put Sedna into this orbit. And we were pretty excited. So we spent like a good decade looking for more objects like Sedna so we could understand the gravitational influence of that star. We didn't find many. I went through an entire PhD student thesis her job was to look for things like Sedna, and she found none. She found a lot of other things, so it was not that much of a disaster, but she didn't find anything like Sedna. But what we found in that time period was maybe even more interesting. All of the very distant objects in the solar system, here's again the Kuiper Belt now, way in here, they're all tilted. They're all pushed off in one direction. They should not be. They should be all around the sun, not tilted like this. And what's weird is that they also are all tilted with respect to the sun. What can cause this? Well, we worked hard to come up with causes, and in the end, there's only one thing that can cause that, and that's a planet. If you have a planet on, I'm trying to get this thing to play here, hold on. play, man. Go. If you have a planet on an orbit like this around the sun, there's again, Neptune is right here. And you have a lot of objects in the Kuiper belt. Every one of these things is an orbit of an object in the Kuiper belt. And notice the number is getting smaller because they're getting ejected by getting too close to a giant planet here. The planet keeps on circling and circling and circling. I'm just showing the orbit. But eventually you're going to find that they all get captured onto one side of the solar system over time. At first we thought that they got captured over here, but we were wrong. They all end up actually being captured onto this side of the solar system. I'm going to fast forward quickly. After 4 billion years, you can start to see that they all are pushed off to one side. They all avoid where planet 9 is. We realized this finally about 7 years ago and realized, oh my God, there's actually a giant planet somewhere out there. And that seeing objects like this in the solar system is telling us that on the other side, there's a planet. In the meantime, since then, these were just a small number, 6 objects. We found more distant objects and they all fit the pattern, except for one, which is actually perfect because only like 95% should fit the pattern. So I'm happy to see one not fitting the pattern. This is a really robust pattern that cannot be explained away. And to date, the only explanation that anyone has come up with that makes any sense at all is a giant planet well beyond Neptune. What kind of giant planet? Well, I'm happy to show Caprice that it is very much like Neptune, her favorite planet. Neptune is 17 times the mass of the Earth. Planet 9, we now know, is about 7 times the mass of the Earth. We know this by doing many, many computer simulations of the sort that you saw, adjusting the parameters of Planet 9, making it a little further away, a little closer, a little bigger, a little smaller. It's this really interesting range between Earth, which is exactly 1 times the mass of the Earth, and Neptune, which is 17 times. And there's nothing else really in between. There's Uranus, but we don't talk about Uranus. So it's exciting to see this new type of planet, not yet see, but hope to see this new type of planet in the solar system. I'd like to point out this is not a slightly larger than Pluto. Let's argue whether it's a planet or not. Here are all these objects in the Kuiper belt that we found over the past 20 years. Here is planet 9. It is huge. It's the 5th largest planet in our solar system. And it's waiting out there, ready to be seen. Where is it? We have predictions of where in the sky it is, and we're searching. We're using big telescopes. We're using small telescopes. We're using pretty much anything that we can get our greasy paws on. I think the most likely place we're going to find it is in this beautiful part of the sky. It's probably my favorite part of the sky. Here's Orion. Here's Taurus. There's this cosmic fight between these two in the sky. And right up above it, in the constellation of Gemini, in the Milky Way galaxy, you can see where all the stars are getting brighter. Our prediction is that this is the most likely place for Planet 9. This is where we're concentrating our telescope power now. We are working hard, and I'd say stay tuned. I think it is likely to be found in the next 2 or 3 years, and we will live in the first era in 250 years where new planets are being found in the solar system. And all those people who now say, when I was a kid, our solar system had 9 planets, you can say to them, yeah, well, it does again, sucker. So that's the quick update. There's a lot more to learn about Planet 9. If you want to learn more, I encourage you to go read some of the other articles we found. But I'm happy to answer any questions you have.
Wow, Mike, that absolutely blew my mind. Our audience has some really great questions. I would like to encourage them to keep asking. But first off, I just need to ask, why was Uranus's first name George? Who is George?
King George, actually, because Herschel was Herschel's patron was King George, and if somebody's giving you money, it's smart to name things for him.
Yeah, that checks out.
The French didn't really like the idea, though, so they kind of objected.
Yeah, that makes sense. So the gravitational models that you showed, beautiful graphics there and visualizations of that data, they show that there likely is this massive 9th planet. We're pretty confident beyond Neptune. What is needed to conclusively prove its existence? What would need to happen?
Yeah, great question. So really, I am as confident that I can be that it exists, but other astronomers are not. I mean, scientists are rightly skeptical about everything until there's definitive proof. The definitive proof could come any day when you actually take out your telescope, point it right there, see it, come back the next night, see it move. calculate its orbit, and you say, that's it. I just found planet 9.
Is it a situation like in biology where if you discover it, you get to name it?
Heck yeah.
Oh, the race is on.
We're going to name it George.
I am in full support of that. Um, one of our viewers asks if measurement bias is an issue in these kind of data sets, and how do you account for that?
Yeah, so to explain what that question is, it's a great question. It's the first question you should ask. So the measurement bias, the observational bias. So we see things basically sprayed out on one side of the solar system. Imagine in a stupid world, we only look in one direction, and then we find everything in that direction, and we say, "Oh, how weird! It's all in that direction and not over here." So that would be an extreme version of observational bias. But there are many in astronomy types of that where you have to be really careful that you're actually understanding how the observations that you made and where you made them, because in astronomy, your observations are affected by the weather, they're affected by what telescope you were at on what night, all these things. And so that was actually one of the first questions we tried to address ourselves. On our first paper, we did a fairly simple calculation, showed that it was not a big deal. But then we have now since then gone back and done very detailed calculations, and the probability that you would get this pattern that we see in the sky just due to observational bias is something like 0.2%. So so there's a 1 in 500 chance that it's just due to chance and bias, and I'm pretty happy to take those odds.
Fascinating. The objects in the solar system in the Kuiper belt or beyond that, you said Arya described it as getting yeeted out of the solar system, getting shot out because of its gravitational pull. Do they extend their orbit, or they're gone? They're no longer in our solar system.
They're no longer in our solar system, and they may well encounter some other solar system a billion years from now. So as you might remember, there have now been 2 objects from outside our solar system that have come screaming through our solar system. The first one was Oumuamua, which is that weird one with the weird shape that people said crazy things about. But the second one, God, whose name I've already forgotten. What was the name of the second one? Comet something. It was so normal that it's hard to remember what its name was. It just looked like a comet. And this is what these things would look like. If this one happened to go by another star and get close enough, it would evaporate and look like a comet. And it happens presumably throughout the galaxy all the time.
Wow.
Borisov. It was Borisov. Comet Borisov.
Comet Borisov. Interesting. As the self-proclaimed Pluto killer, what do you make of people's emotional connection to the dwarf planet, causing them to kind of stand up for Pluto's planethood?
I get it. It's hard. I think of the solar system as the largest neighborhood that we understand, right? So pretty much everybody can tell you the order of the planets and has a view of what they are. And often if you ask people, okay, so what's beyond the planets? The answer is the galaxy, the universe, a black hole, not sure. So like in most people's minds, the solar system is their neighborhood. And so to say that something is not the important part of their neighborhood that everybody grew up doing, I get the nostalgia. I feel nostalgia about it too. But I would argue that one slide that I showed that really shows how incredibly small Pluto is and how much it fits with the rest of the population. It just shows you that if we didn't know about Pluto and we found it today, there is zero chance we would call it a planet. It really is just a coincidence plus nostalgia that makes people talk about it today.
Yeah, definitely. Do you think part of that is just like poor science communication, like in the decades past that showed Pluto among the other planets lined up like kind of
sure.
stature that was a part of that?
My daughter had a lunchbox when she was in 2nd grade with planets on it and with Pluto as a planet, because my friends loved to give me things that had Pluto as a planet on them. And all the planets are close to the same size. Jupiter is a little bigger than Saturn, which is a little bigger than the Earth, which is a little bigger than Pluto. But if you saw that real one, it's like there is no size comparison. Pluto is 250,000 times less massive than Jupiter. It's just not a major part of our solar system that deserves to be singled out as something, planet like these other big things.
Yeah, and the visuals you showed definitely made it clear for me. As Mitzi says, I wish you had been my astronomy teacher. I actually feel like I would have learned a lot more.
Yeah, I'm gonna have to go give Caprice a talking to though, because she had Pluto as a planet on her first slide, so she's now on my enemy list. I don't know.
Oh no. No, we're only making strong
Okay.
connections and friendships here
Oh,
on
okay.
Night School
Okay.
tonight. Thank you so much, Mike, for giving us this amazing presentation.
My
Up next
pleasure.
and up last, we will hear from Christian Contreras. Christian, your audio is not connected, unfortunately.
There we go.
Much
Can you hear me
better.
now? Oh,
Yep,
perfect.
go for it.
Hey everyone, my name is Christian. I work at the California Academy of Sciences inside the Morrison Planetarium. And my job is I'm a planetarium presenter. So I've been doing this for about 6 years. And all I do is inspire wonder and awe to folks just like you to go look out into the night sky and learn more about astronomy and space. Um, I love doing this job. It's so much fun. I've seen so many different encounters. But what I'm going to do for you right now is I'm going to do you a quick tour of the universe. It's one of my favorite shows that we do inside the planetarium. Pretty much, we're going to be starting off pretty close to the Earth, and then we're going to be zooming all the way out to the very edge of the observable universe. This show is normally 30 minutes long. I've got 15 minutes, so we've got a lot to cover in the next 15 minutes. So I'm going to jump right into it. So, like I said, we're going to be starting off pretty close to the Earth. We're starting off at this really cool spacecraft called the International Space Station, or the ISS for short. And a lot of people tend to ask me, like, hey, Christian, what is this thing? I always see it in the news and articles, but I don't really understand it. Turns out the International Space Station is a research facility. It's a laboratory that orbits around our planet Earth. And they conduct so many different types of science experiments up here. Many cool things have been discovered and created here at the International Space Station. Highly recommend looking at the list. It's vast. And also, what's really amazing is that this thing looks really far away from our planet, but the International Space Station is only about 225 miles above the surface of our world. So 225 miles for Americans, that's like not too far. And what's really fascinating is that this thing is traveling incredibly fast. The International Space Station is traveling at 17,000 miles per hour, where it orbits once around the Earth every 90 minutes and it experiences 16 sunrises and 16 sunsets a day. Very romantic. And this also looks really huge, but it's not that big in actuality. It's only about the size of an American football field, so not too big. But to tell you the truth, folks, this is as far as we put humans into space nowadays, only 225 miles above the surface of our world, because traveling into space is quite costly. But we're going to see the International Space Station slowly disappear to the city lights down below. And before we lose track of it, I want to add a nice little orbital path so we can see it as it slowly fades away. And it looks like we're just above Europe here. And now we're able to see our entire planet Earth. And now that we got a nice view of our Earth, I just want to let you know that the space program or the software that I'm using here is something that you can download at home. We're using a software called OpenSpace. So if you go to openspaceproject.com, you can download this, and it's such a cool software. It's open source, so that means anybody can add to it if you want to be a contributor. New things are being added to it all the time, and I just love flying through the universe and showing my friends and family this. So very cool software. Highly recommend checking it out. OpenSpaceProject.com. But now that we got a sense of what we're using in here, let's make our way over to our nearest natural neighbor to us in space, the moon. And folks, we humans have been to the moon before. That was between 1969 and 1972, thanks to NASA's 6 Apollo space missions that brought a total of 12 incredibly lucky guys to walk on the surface of the moon. They got to conduct science up here, and of course, they had some fun. They got to play some golf. But again, last time we sent humans to the moon was 1972, a little more than 50 years ago or so. But don't worry, folks. We humans are making a return trip back to the moon in the next few years, thanks to the new NASA space mission called Artemis. So we should be having humans back to the moon in the next few years. Hopefully, everything goes according to plan. Look out for any news about that. And what's also really fascinating is that the moon is really, really far away from us. It looks relatively close, especially when it's close to the horizon. Feels like you can reach out your arms and touch it. But the moon's about 240,000 miles away from the Earth. Whew, 240,000 miles, folks. Some of the adults watching this program may have a car with that many miles on it. And if you take better care of your car than I do, you can even imagine driving to the moon if you drove for about 4 months nonstop, going about 80 miles per hour. Although we don't recommend that, the roads out here are poorly maintained. He he he. And from here on out, folks, we're gonna need to use a more useful measuring stick because at this scale, using miles is like using inches to describe the distances between cities because space is so big. Astronomers instead use a more convenient measurement known as light speed. And light travels at a mind boggling speed of 187,000 miles per second. That's roughly about 300,000 kilometers per second. So while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so or since, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like a short pause in conversation. But now we're going to leave the moon behind, so we're going to see it slowly fade away, just like how we saw with the International Space Station earlier. And just like before, I want to add some nice planet trails to keep track of everything, because again, space is huge. And on our quick journey today, folks, we're going to be traveling much faster than the speed of light. We're going to be traveling at the speed of the human imagination, thanks to computer models like OpenSpace showing us the most accurate images and information available to us. And now the nearest star to us, the sun, comes into view. So here comes that sun. Do, 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 do. And folks, our sun is incredibly far away as well. It's about 93 million miles away from our planet Earth. 93 million miles, that's a good distance. In order for sunlight to travel at 93 million miles, it takes sunlight about 8.5 minutes to cover that distance to hit our Earth. So quite far. But now that we have a nice bird's eye view of our solar system, I want to just go do a quick refresher of what we have. I know our speakers before covered them, but just want to make sure. Right in the middle, we have our star, the sun, the biggest thing by far. Closest planet to the sun, we have Mercury. Then we have Venus, the really hot one. Then we have Earth, that's us. And then Mars, the red planet. And of course, beyond Mars, we have our main asteroid belts. And this is what it would look like if I highlight all the asteroids in the asteroid belt. There's about a million of them here or so. And past the asteroid belt, we have the really big planets. We have the gas giants. We've got Jupiter, the largest of them all. We've got Saturn, famous for its rings. And then we have Uranus. These are the icy gas giants. And then now we have Neptune. And of course, we can add everyone's favorite land lovable dwarf planet, Pluto. I love that I just did a stream with Mike Brown, the Pluto killer. So that's so cool. But here's the orbit of Pluto, very different from all the other orbits. And as you heard before, Pluto is no longer a planet. It's now a dwarf planet, and it hangs out here in this region in our solar system called the Kuiper Belts. And this is what the Kuiper Belt would look like here in our software. And the Kuiper Belt's like a second asteroid belt where you're mostly going to find our icy asteroids and short period comets, comets that don't stray too far away from the sun. But I want to put away the Kuiper Belt because that's just a whole lot to look at. And now I'm going to be putting on screen some many different spacecrafts we sent out to explore our solar system in the 1970s. We have the trajectories of Pioneer 10, Pioneer 11, Voyager 1, and Voyager 2, and the latest of them all, New Horizons, which did a quick flyby of Pluto in 2015. You can see that interaction of that spacecraft flying by Pluto's orbit. Now, all of these spacecrafts are all traveling fast enough to escape the sun's gravity and leave our solar system behind. But even the most distant of these robot adventures, Voyager 1, has not traveled as far as light travels in a single day. In order for sunlight to travel all the way out to the orbit of Pluto, it takes sunlight about 5 hours at the speed of light. 5 hours. That's not too bad. But now we're going to leave our planetary scale behind, and now we're going to be heading out into interstellar space, the space between the stars. Distance now becomes so immense, it's going to take us about 4 years at the speed of light just to reach the next star system to us, the Alpha Centauri system. And it looks like we see Alpha Centauri on our far right. So you can see that star that's kind of moving much more closer on the right hand side of our screen. And again, 4 years at the speed of light just to reach the next star system to us, folks. But that doesn't put into perspective how long it would take us to travel that distance. Well, if you're getting a rocket ship today, make your way over to Alpha Centauri. It's going to take you roughly about 8,500 years to make that trip. Whew, and that's just a one way trip, folks. But let's stop consider whether humanity has made its presence known beyond our solar system, because now we're going to be stepping inside something called the radiosphere. And again, we're now inside the radiosphere. And this represents the current limits of the most distant radio signals humanity has ever broadcasted, or rather leaked into space. And it extends about 90 light years in all directions, emitting out from the Earth. This first began in the early 1930s with strong radio waves, early television, radar signal, and then later the detonation of atomic weapons. All this stuff is emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. And humans were broadcasting well before that, but the earliest radio was not quite powerful enough to escape the Earth. Since all these signals are electromagnetic, they are traveling at the speed of light. So this is kind of like humanity's electromagnetic footprint in the universe. And of course, the radiosphere is constantly expanding at the rate of 1 light year per year. So is anybody out there listening? And now, folks, I'm going to be adding these many markers onto the screen. These many markers indicates many thousands of stars astronomers have discovered over the last 30 years, which has at least one or more planets orbiting around them. We call these planets exoplanets. And we're looking for any of them that are Earth like with conditions suitable for life as we know it. And so far today, we found more than 5,000 confirmed exoplanets in the nearby vicinity to us, 5,000 of the worlds besides our own. And that number is going to be increasing as the years continue because new space telescopes are being developed as we speak. So they're going to be scanning more and more of the night sky, finding exoplanets left and right. Now, to say if any of them are Earth like with conditions suitable for life as we know it, well, we cannot answer that question quite yet. But like I said, new telescopes, space telescopes are being developed, so we got to wait. But the more important point here is that quite a few of these planetary systems are within that 90 light year limit of our radiosphere and could have potentially received our signals. However, since radio waves travel at the speed of light, if there is anybody that's out there able to listen in and answer back, the communication delays between hellos could be decades in time. And of course, planetary systems beyond the radiosphere, more than 90 light years away, have not heard from us yet, but eventually they will, as the radiosphere is always growing, but it becomes weaker as it does. And now I'm going to be putting away those exoplanet markers, but I'm going to leave our radiosphere up on screen because as huge as humanity's electromagnetic footprint is, it is nothing compared to our Milky Way galaxy. And now, folks, we're looking down on our Milky Way galaxy. This is the galaxy that we live in. And of course, I have to ask, can anybody see their house from here? And folks, our galaxy is incredibly large. If you wanted to cross it from one side to the other, it's going to take you about 130,000 light years to cross it. So it is enormous. And our Milky Way is so huge, we estimate that there's at least 300 billion stars in our galaxy. If our recent discovery of so many exoplanets just within our small neighborhood within this vast star city is any indication, there could be billions of planets and potentially millions of Earth like planets throughout our single galaxy. And before we leave the Milky Way, I need to show you what it looks like from the side. You're going to notice that our galaxy is this really big flat spiral disk. So it kind of looks like a big pancake in space. And this is important because when astronomers want to learn and look out into the universe, it's so much more easier for them to point their telescopes galactically north and galactically south instead of looking through the plane of the Milky Way, which has planets, stars, gas, debris, things that block their view of the universe. So keep that in mind. We like to point our telescopes galactically north and south instead of looking through all that debris. That's going to come important in just a little bit. But folks, the Milky Way galaxy is only one of many hundreds of billions of galaxies that comprise the known universe. So in this giant leap, every single point of light that you're now going to see no longer represents a star, but rather the location of an individual galaxy. Each galaxy containing hundreds of billions, perhaps trillions of stars. Now we live in a local galaxy group which contains about 30 galaxies large and small, also includes the nearest large spiral to us, the Andromeda galaxy. And the Andromeda Galaxy is only 2 million light years away, just next door, and heading right for us. We're going to get to know it pretty intimately in about 5 billion years, so mark your calendars. And as our picture continues to expand, you're now going to realize that galaxies are not evenly distributed throughout space, where there's one galaxy here, another galaxy there. Instead, galaxies like to clump together in large groups and clusters, or they create voids where there's very few galaxies or no galaxies at all. So you can kind of think of galaxies like people, they like to hang out together or they like to avoid each other. And folks, we've zoomed so far out now, this picture that we're now looking at represents the closest 30,000 galaxies to us in a space over 300 million light years across. We got to give thanks to an amazing astronomer by the name of Dr. Brent Tully, who worked at the University of Hawaii, who compiled this amazing representation over decades of time alongside dozens of other astronomers. So shout out to Dr. Brent Tully. I love flying through this galactic map. But now we have automated systems that are mapping even the most distant galaxies. So now we're about to see the large scale structure of the universe. And remember, folks, every single point of light that you're seeing, that's not a star, that's an individual galaxy. And by the way, the large scale structure of the universe is not in the shape of a bow tie or butterfly. Remember when I mentioned that we live in a big flat spiral disk of our Milky Way galaxy? Well, if we were to line it up, it would go right down the middle of our screen vertically. So again, we like to point our telescopes galactically north and south instead of looking through the plane of the Milky Way, which of course blocks our view of the universe. But let us continue pressing on because I still have a little bit more before we wrap up our show. And now, folks, we're going to be encountering these really distant, faraway objects known as the quasars. Now, quasars are short for quasi-stellar radio sources, and these blazing objects are all billions of light years away. These are these orange dots that we're seeing here on the outer edge of the large-scale structure of the universe. So now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenage version of the universe. And before there was a teenager, there was a baby. So let's press back to a time before planets, before stars, and even galaxies began to form. Folks, we're about to see the very edge of the observable universe. And here we are, folks, at the very edge. And what we're looking at is something called the cosmic microwave background image, or the CMB image for short. All evidence indicates that the universe that we live in is about 13.8 billion years old. This is data compiled by Planck and other radio telescopes. And this is a very baby version of the universe, only 380,000 years after the Big Bang occurred, where space and time began. And this isn't your typical photo either. Instead, this is a temperature density image where the light echoes of the Big Bang are color coded, with the lighter areas corresponding to the hottest, least dense regions, and the darker areas, the coolest, densest regions. These fluctuations in temperature and density are extremely tiny. They vary no more than 1 part per 100,000. But these tiny differences eventually gave rise to that large scale structure of the universe that we saw moments ago, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. Though our view here is at the outer edge of the known universe, folks, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But we've gone as far back as the law of physics can physically allow us to go, so we only have one direction left to go, and that's going to be back home towards planet Earth. So let's find a nice entry point through all these quasars and galaxies, and let's make our return trip back to planet Earth, everybody. And folks, we are crossing an expanse of over 13 billion light years. We're presenting you this view of our universe and the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. We live in a golden age of astronomy with new generations of telescopes and spacecrafts that are extending the reaches of our eyes, preparing for the eventual race between the advancement of technology and the accelerating expansion of the universe. And with that thought, I want to remind you all that astronomy is for everyone. You don't need to be a rocket scientist to enjoy the beauties and wonders of our universe. All you need is the night sky, and if you can, get away from the lights of our cities and look up. Even a good pair of binoculars makes for a decent first telescope, and there's astronomy clubs all around the world that invite people just like you to peer into the great beyond, allowing you to see what the universe has to offer. Now, astronomy as a hobby can offer an endless supply of satisfaction, and I do hope you'll join us, those who dream amongst the stars. But it looks like we made our way back into our Milky Way galaxy. We're heading straight through that radiosphere. We're making our way back to our star system, the solar system, our little neighborhood in the vastness of space. And now we're about to pass those spacecrafts we sent out in the 1970s to explore our solar system, passing the orbit of Pluto and the Kuiper Belt region, and making our way to the third rock from the sun, our homeworld planet Earth. All the people that we know, love, ever learned about in history all lived on this one planet. And now we're about to pass the orbit of the moon, the furthest we've ever sent humans out into outer space. And with that, folks, as we make our final approach back to planet Earth, that's going to be the end of our Tour of the Universe show. And again, we're back in time, just in time for dinner time, and ready for Q&A.
Hey Christian. That was amazing. Darian and I were sitting in the backstage with our hands up while we were zooming back into Earth, like wee, like a little roller coaster. It was so much fun. Yeah, that was amazing. Uh, so okay, we have a lot of questions. Open space is so good at conveying that like sense of scale, and I feel a lot of existential like wonder and dread when I think about how big the universe is. How does it make you feel?
After the third show, the existential dread is gone, but I am constantly exposing it to all the guests who come and visit the planetarium. You can tell folks are just like, my daily problems no longer matter because I'm now thinking about how small I am in the universe. So it all comes to perspective, I guess.
Amazing. Yeah, so delightful. And so I mean, this software is so cool. At what kinds of data and information do people contribute to it? And like, can anyone contribute really? Like,
Yeah, so the software was put on or created by NYU graduates. It was one of their senior projects. And this was really fortunate because at the time, the normal space softwares that we're using went out of business. So they were creating this. And what's really cool is that Open Space and the Morrison Planetarium work together to help create new content. And so it's open source. That means anybody can add to it. If you love visuals, graphics, you can add whatever you want. Some people add update like exoplanets. People make artistic renditions. You can help place objects. Some people make spacecraft models. We have a really cool JWST image model that we use all the time in the planetarium. So honestly, if you want to contribute and you're good at that stuff, definitely do it. There's so much cool things that you can do with open space.
oh, that's awesome. Yeah, that's amazing. And this is kind of a shift into like personally, I'm kind of a space newbie, space noob, if you will. Um, are all galaxies flat? Like you said, the Milky Way is flat. Are all galaxies like that?
No, not all the galaxies are the same. There's different types of galaxies. So we have our spiral, that's our Milky Way galaxy. And first off, I want to say we humans have never seen our actual galaxy. We've never sent a spacecraft outside to look back. What we're seeing is an image of Andromeda. That's the closest one to us, and we think we have a similar galaxy structure. So we just steal the image of Andromeda. We've never seen our own Milky Way. But that's one type of galaxy. Another one is just two arms kind of spiraled out together. And then there's an open one. So it's a galaxy that's just kind of a diffuse ball. So they come in different shapes and sizes.
That's so cool. And why is that? Like, what makes that happen?
Ooh, it's different evolutional processes. And I think it depends on where they formed in space. To be honest, I don't know a whole lot about galactic formation, but it's out there if you want to learn more about it.
Yeah, I mean, it sounds like a doozy, honestly.
Yeah.
So, yeah. And you mentioned like astronomy clubs and getting involved. Like, do you have any tips of how to get involved?
Oh, there's so many. I know a lot in the Bay Area. So if you're in the Bay Area, there's the San Francisco Amateur Astronomers, and they are a great group of folks. They have star parties. Star parties are where people just come and bring their telescopes to a dark, secluded area of the city, and they make observations. They'll look at planets. They'll look at different constellations, whatever's up in the night sky, and they all get together. So they're a great group of people. I also know that many universities have planetariums. They're relatively small and they have observatories. So if you look in your local area, search up nearest planetarium, nearest observatory, look up star parties, and I'm sure you can find a lot of cool folks.
Like taking notes on the side, like, okay, star party. Like, go look up. Um, that's so cool. And how did you first get into astronomy and space?
Oh, that's a good question. I grew up in the middle of the Central Valley and it was all just fields. And so when I went outside, all I saw was the night sky and hearing crickets. And honestly, I just fell in love with the night sky and I just wanted to learn more about it. So I told a lot of folks, I'm going to go study astronomy. And then folks are like, what are you going to do with that? So went to San Francisco, studied physics and astronomy, and met a lot of cool people. And I got a position at the academy, and I've been working at the planetarium for about 6 years. And it's one of the most fun things I've ever done in my life. I just inspire awe to all the folks, and I get to hear everyone's lovely questions, and I get to answer those questions and get a better sense of the universe and space.
That's fabulous. I love that. And one final question. Do you have a favorite star slash planet slash exoplanet slash outer space object?
Ooh,
Maybe I don't know. Like,
there's so many. That's a really hard question. I mean, there's so many objects out there. One of my favorite things at the moment is pulsars, and pulsars are these leftover remnants of a star after it explodes. And pretty much it's a really condensed star that's really, really heavy. And they're called like space lighthouses because they're shooting out beams of high energy, and they spin really fast, like lighthouses. And if you were in the path, you would be totally irradiated. You wouldn't be around for too long.
oh
But
no.
the coolest thing about them right now that's happening in astronomy is that they're using these pulsars on either side of the Milky Way, and they're using them as kind of like measurements because they spin so regularly. They can keep really good measurements like that. And so what folks are doing right now is they're measuring gravitational waves. These are waves that ripple through cosmic space after two stars merge into each other and explode. And so it's kind of like throwing a rock in a pond, and it sends out waves into space. And so they're using these pulsars to see how big these waves are. And these waves pass through Earth, and they kind of everybody on Earth, molecularly wise, kind of expands and contracts together, which is just so cool.
That is so wild. Oh my
Mhm.
gosh. Yeah, that's a really good favorite. Well, thank you so much for being here, Christian. And folks out there, Christian and their team do like a tour of the universe every week on the very same YouTube channel that you see Night School on. So you should go catch it. When are those?
Those happen every Wednesday at 4:30 p.m. Pacific Standard Time, and I'm usually the one doing the show, so you might hear my voice.
Yeah, yeah. So go check those out for sure. Um, and yeah, thanks for being here. I'm gonna bring Darian back up and close out for the night.
Take care, y'all.
Thank you so much, Caprice, Mike, Christian, for like a stellar night of interstellar learning. And thank you, of course, for watching. Do you feel small? I feel small.
Yeah. Understatement of the year.
Big time. I hope you feel a little more inspired to do a lot more looking up. I mean, outside, at night, ideally.
Go find a star party. Yeah, go find a star party.
I'm Googling it right now.
We here on Night School, in the meantime, after you come back from your star party, are live on the third Thursday of every month, which means that we will be back here on August 17th with an episode that we're calling Night School Bedtime. And it's not the bedtime that you're thinking of. This time we're talking riverbeds and mussel beds and so much more. There are so many amazing beds in nature. And we are so excited that we can hardly sleep.
While you're anxiously awaiting our next episode, might I recommend subscribing to the California Academy of Sciences YouTube channel? If you do, you'll be notified every time we're back. There, you can rewatch past episodes, including this one, on our YouTube channel for free, anytime, from anywhere on Earth. Or, I mean, on the off chance you're on the ISS, from outer space.
Thanks again for joining us tonight. Take care.
Bye.